leave it on to Mark.
Thank you very much. First of all, why are we here on a Sunday morning? I've been moaning to Belinda for about 5 or 6 weeks now. Are you sure it's on a Sunday? Are you sure? What time is it? So I can now come and blame all of you as well for saying that you'd come along. And I can't believe how many people there is here on a Sunday morning. My Sunday mornings are very precious to me. I suppose it's a quiet time. There's no one driving their V8s to the supermarkets and whatnot, so I can make a nice cup of tea, usually Tetley. No one needs to drink Lipton. It's absolutely horrible. I stew a tea bag for about 5 minutes, 2 sugars, and you have to stir it when you initially put the sugar in. My daughter doesn't, so you get that huge slosh. It's like a Farmers Union iced coffee when you get to the bottom. And I walk around the garden. Usually on a Saturday, I'd be out in the garden. I'd do all the trimming around the stones on the edge of the grass, and I'd mow my lawn. And it's a very close little neighbourhood. It's like neighbours. We've got Scott and Kylie across the road, Greg down the hill, Tony, but he works shift, so we don't see him that often. And I go out and I look at my grass, possibly my most cherished possession. My daughter says that I love my lawn more than my children, and that's why she's my second favourite child. But I'm slowly getting her into the garden and whatnot, which is kind of helping. I have to pay her, obviously, to pick weeds, and then she gives up halfway through and goes off, and it's a nightmare. You know what children are like. But anyway, we're going to delve down into it. Scott, my neighbour from across the road. So it's about perception, I suppose, and about Deirdre's talk as well, about human perception. So which lawn is the flattest? Which has the best surface roughness? And by surface roughness, I mean from the top of the grass to the soil. If you drew a line through one of those lawns and you measured every one of those points and took an average, you'd get the RA, it's the average roughness. And it's quite deceiving, actually. You can see on the part of micro machine down the bottom, which is a hot embossing tool for DSTG. You can see all the lines, and it's basically the same as mowing my lawn. It's just working out the optimum pattern. I obviously work out the optimum pattern for going around my lawn to be the most efficient and give the nicest pattern. But it's very deceiving because that actually has a better surface roughness than the diamond machine part. It's just that with the diamond machine part, we get a very good finish. Because the cutter is very, very sharp, and we're shearing material away from its parent block, it leaves a lot nicer finish, but it's actually twice the roughness of this part. Also a good point, how do we know? Unless you get down on your hands and knees like Scott and inspect every piece of grass in a line, it's very difficult to work out. So it's, I suppose, what's important to you. You all have parts you want to make, and you need this and you need that. But truly trying to achieve the best flatness and surface finish, surface roughness and the form is very extremely tasking. And we're going to talk a little bit how we achieve them and the type of equipment that we use. But I do literally spend most of my life worrying about these things or trying to achieve them. But thanks to Deirdre now, who's been the catalyst for us going into the monocrystal diamond tools, it's pretty much my timeline here has been cut in half, and it's pre-Deirdre and after Deirdre now, because now I use the diamond tools for everything. I can run them 40 times faster, and they give me this finish I could only dream of. They're obviously very expensive and take a long time to get here from Europe, but we obviously pass those costs on to you. Here's 2 of our pieces of equipment. You're going to hear from Ben later and Ben Johnson from Macquarie about some other pieces of equipment in the know, and I think you're going to go off for a tour with Evan later on. So it's all similar types of equipment. We've got the Kira CNC mill. We got that about 10 years ago. And they actually had to get special permission from the Japanese government to take it out of Japan because they saw it as intellectual property. It's basically it runs on linear motors. It's basically running on magnets. It uses a litre of oil every 18 months, and the rest of it runs on air. We can put small tools in here. It's got 2 spindles. We can run them up to 160,000 RPM. So that's about 2,222 times a second that's rotating. The trouble we've got with the Kira is it's old and it needs a bit of looking after, and our main problem is temperature control. We buy some rather expensive tools from Japan, and they gave us a case study before we bought the tool and said that they were machining something. Someone entered the room while they were machining. Their body temperature caused the room temperature to go up by 1.9 degrees, and in turn the spindle actually expanded by 4.3 microns. And we're trying to get down into that micron realm. So if I can warm that up overnight and get it thermally stable, then fantastic, then no problems. We can get down within those sort of micron tolerances, which is quite unique for the Southern Hemisphere. There's only a few pieces of equipment around like this. And we've recently just got William McAdell, which is a 7-axis turn mill from Switzerland. So we started using diamond tools on here as well. This being a new machine, they firmly characterize every aspect of the machine so it knows when the spindles say running at a certain RPM, what the expansion will be. So we put two tools in here, and we machined a part that you see later on, and both the tools machined the two surfaces within a micron of each other. So it's moved quite a long way in those 12 years or 10 years since the Kira was made. The next generation is probably 200 times more accurate than this, and we can move, I think it's 10 million increments before we get to a millimeter. So before Deirdre, we used to use these sub-micron grain carbide tools. We still use them, but we always end up finishing with the monocrystal diamond now. And you can see in the horrible yellow color there, that's a 100 micron cutting tool. And it's got similar fluid geometry to like a drill you buy from Bunnings, basically. We can put coatings and things like that on there. The one by the customary possum hair is 5 microns diameter. So we can put that in the Kira and we can cut 5 micron channels there within a micron accuracy. We're usually removing about half a micron at a time when it comes down to a tool that size. But now we've got the single crystal diamond, which is a lot sharper. Although it looks very weak, it is extremely strong. Like I said before, we can run it 20 or 40 times faster and achieve some beautiful finishes. But this would all be nothing without in this instance, our OLS laser confocal microscope, because if we can't measure what we make, we really don't know where we are. So this needs to be the most important piece of equipment, the most accurate out of everything in the process, just for us to truly understand what's going down, what's happening in that sub-micron layer. You can't really see this too much, but there is little variations on this surface of another machined, of a diamond machined pattern that we've made. And the surface roughness, this is an SA because it's a 3-dimensional view. If it was a single line, it would be RA, the average roughness. And this is actually 177 nanometers. But you've still got that optical finish. That might still work for you. So you might not need the surface roughness if you've machined it with a diamond and it's sheared it off that cleanly. The one on the right-hand side just gives an example. I think that was 13 nanometers. As Deirdre said, we've got down to 7. I think the part in the middle was around 100. If that was machined on a conventional CNC machine, it'd be around a 300 or 400. And most nanometer roughness. And most machined engineering drawings will call for a roughness of about 1.6 microns to be a good finish in general machining. So we're right down in the pain and misery and the grey hair and trying to achieve that really tight tolerances and high surface finishes. So here's some of the parts we've made. We've got some pre-Deirdre and after Deirdre. We've got a pyramid electrode that we made for a researcher at Adelaide Uni, which is an interesting story. So it's an electrode for a microplasma reactor to extract precious metals from meteorites to use as fuel in future spacecraft. So as they're going through space, they can harvest these meteorites and stuff laying around and extract whatever precious material they can from it to use as fuel. We've got a PMMA lens up in the top right-hand corner that we're making at the minute. It's literally on the machine now for Deirdre. And we're just exploring how good a surface roughness we can get on this machine and on PMMA, because we're going to make some lenses for Deirdre. I've got a little probe here with a possum hair tied through the middle. So a possum hair is about 92 microns in diameter. We've gone down to about half that size now with these parts. So we're not only making small features on large substrates, but we're making small parts as well. That's part of a larger assembly. And if you can see down here in the corner, these little discs, I tried to make these on our CNC machine, but because we've got a lot of force when we're shearing material away from its parent, basically, because we've got a lot of force, they're an absolute nightmare to make. So we sent those to Bennett Macquarie, and they're relatively straightforward for him because his laser machining doesn't put that kind of pressure on it, so you don't need to hold it as rigid, and we didn't get burrs. These horrible little uncut pieces of material on the edge of features. In the middle here, we've got a stepped lens. So from the outside to the middle, there's about a 3.4 micron step, but that's in 100 nanometer steps. We did that as a test piece when we moved the Kira just to check everything was okay. Before Deirdre, if we wanted to achieve a really good surface finish on things like molds, we've got an aluminium mold here. We actually used to hand polish, so we'd go down the pain and the misery and the diamond solution until we got down to like a mold skin with a 1 micron diamond solution. And we could get down to about 40 nanometers, which is good enough for injection molding. The surface limit of the material we were molding, which was PMMA, was about 20 nanometers, so we could get that clarity that we needed in the mold. We've got some more diamond machine up here on a high aspect ratio flow cell. This is what we've machined recently. So there's a little part on the end of here. We machined this with a very sharp diamond tool. So the part diameter is 250 microns. And we machined a parabolic mirror in the end of it. And with the new machine, we were able to hold that, separate it from its parent material, reorientate, and then machine a feature in the back of it to accept a fiber. And this is going to be part of a larger assembly. But the fact we're able to hold it and reorientate it, was quite impressive. So what is surface roughness? So we all have a form. If you're making lenses, that'll be your hemisphere, your concave, your convex structure. So that's what you want to make. Waviness, Greg down the bottom of the hill, he's retired. He'll have a few glasses of Chardonnay and he'll get on the lawnmower and you'll see that waviness in the lawn. But he doesn't care because he's retired. Usually, though, it's a machine-induced repetitive feature. So it'll be something down to the frequencies you're running at, the resonance of the machine, if the tool is vibrating. If you make small parts on the same machine all the time, then you'll have slight wear in some of the rails that it runs on. So these all make up surface roughness, but the roughness is actually that texture on the surface from the top of the grass to your soil. And that's about it. And you can all have morning tea now.
Thanks, Mark. Hope you got your gardening fix combining
I couldn't mow the grass yesterday, and now it's rained, so like in all kinds of trouble.
But, thanks for making it exciting for us and giving up your Sunday morning. Got a question here?
So you mentioned that this produces a lot of shearing force. So does that stop you using this for crystals and stuff like that?
We have machined some crystals. The trick is to encase them in something so you don't get that breakout. Evan's got a machine here, an ultrasonic mill suited to machining those very brittle materials or hard material, because the tool that he uses reciprocates, so it's ultrasonically moving up and down while it's rotating, but I won't steal his thunder. But we're constantly aware of that breakout, that chipping, like anything glass or ceramic I send to Evan. Likewise, anything really thin, we usually send to Ben because he's doing more 2D or until he gets his 5-axis machine anyway. We can machine it, but it's measuring those chips. We got some special tools from Japan to machine optical fibers, to machine various features on them. And they actually gave me a warning again because they said their precise tool requires you to remove 2 nanometers of material at a time. Which I was quite shocked actually. Their medium range one was 2 microns, so that's more within our realm. So we brought that and we were able to reduce the chips to within like 10 microns or something. But
So just following on from that, so people try to make mirrors at the end of optical fibers using CO2 lasers and stuff like that. Can you actually machine into?
I'd probably say yes, and then my boss would shout at me and say, "Why have you wasted all this time doing it?" But he's not here. But I'm sure Ben does some similar things to that. It depends on the design. We've kind of just started off in that realm. Just removing that amount of material may harden the fiber slightly, but we need to kind of look into it. But in theory, Ben's pulling his face. But
no, the CO2 Vitrans is very neat, but it's using the surface tension of the glass to form the curvature. People have done some really, really neat stuff by writing the optical assemblies on fibers using things like the optoscribe as well. And that's probably more applicable to the workshop that's happening across the road, but very nice 2-photon lithography writing of whole optical assemblies on fiber tips and things like that. So, but if there's a real niche need to try and machine something like that, that would be a challenge.
Yeah, I've more grey hair.
We have such machine which measure the liquid mirror surface roughness.
Liquid meter surface roughness?
Liquid mirror surface roughness.
With a liquid, like you measuring the surface roughness of a
like
liquid. If it was very stable, we've had people ask in the OLS before, if they can look at liquids within their device, and you can measure it, but it will do some funny things, and you may need to put in, like if we do clear polymers, you need to put in the refractive index and things like that. But you could possibly do it. If you were to email Belinda, we might be able to pass you on to some people who can. Yeah.
With the help of refractive index, it is possible.
Possibly, yeah. I won't say definitely, but yeah, it might be. It's worth asking the question to someone like Olympus.